Okay, so in the last lecture, we discussed the general solution to the system with azimuthal symmetries, and we use the spherical coordinate for that approach. You can see that the solution is actually very compact. It has two forms. It has two parts. The first is the radial part, and the second is the angular part. And in the first example, we specify the potential on a surface and calculate the V both inside and outside this surface. So we find out that the AL is actually responsible for the potential inside surface, and the BL is responsible for the potential outside the surface. But also there are special cases where if there is an external magnetic field, this magnetic field might be changing the boundary conditions on the outside. And somehow it's possible to bring out additional A1 into the problem, and you have to be careful about this. Also, in the last example, we don't specify this potential. Instead, we specify the charge on the surface. And this time, we want to determine the potential both inside and outside. And we use the two equations to calculate the ALs and BLs. So first, we say that the V itself is continuous. And then that gives us one equation relating the AL and BL. And then we say that the derivative of this V is actually not continuous, and the discontinuity is determined by this difference determined actually by the charge on the surface. And so here, this combining the two equations, or actually more precisely speaking, two sets of equations, because there is two equations for each L. And after we combine all these equations, we will be able to determine this AL and BL. Okay, so today now I want to discuss the multiple expansion. So I've heard someone asking, say that for a problem, you might not be, when you are deriving the results, you might not be easy to strictly follow the math, and sometimes you miss a term. So how do you know if your results are correct or at least reasonable? So one possibility is to do a dimensional analysis. So you can check your final dimensions for your expression, check if they have the correct unit. So another way is to make some approximation or take some limits. So you can take the far field limit, which is when the R goes to infinite. And so here, this multiple expansion is exactly doing this. So in the multiple expansion, we are trying to figure out what is the far field expansion. So here, starting for a single point particle. So for a point particle, we are very familiar that the electric field must be decreasing as 1 over r squared, and correspondingly, the potential should be 1 over r. And we also calculated the two special cases, so both in the second lecture and in homework 1. So in homework 1, we calculate the far field distribution of two spheres. So there is one sphere, or a solid sphere with charge density rho, another solid sphere with charge density minus rho. And we determine what the far field expression looks like. So do you still remember that? What's the order of the V proportional to? Like, is that V proportional to 1 over r squared? Okay, so if you forget, the answer is 1 over r squared, and the E here is proportional to 1 over r cubed. You can look up your homeworks. And also in the lecture 2, we also calculate this configuration. And at one at the axis with plus q charge, another at a slightly different location with minus q charge. And we also determine what the far field E looks like. So at that time, we only calculate the electric field, which is 1 over r cubed, but correspondingly, the potential should be 1 over r to the power of 2. So as you can imagine that here I can get to slightly different setups of charge distribution. Say I can put we can put one plus charge here and another charge, negative charge here. So this will give us a far field distribution of 1 over r squared. And now if we put an opposite case of that, this will also give us 1 over r squared contribution in the far field. But these two terms combined together will cancel each other. And so this 1 over r squared is actually not the correct leading order for this configuration. And we name this as a quadrupole. And the V here is actually leading order is 1 over r cubed. And for a single charge, we simply call this as a monopole. And for a two-charge configuration, we call that a dipole. So we can even go to higher orders by simply combining two quadrupoles together. So one you can see is on the upper plane, one is on the bottom plane, but the charge of them are slightly flipped. And in this case, there are no 1 over r cubed term contributing to this charge configuration. Instead, this leading order is 1 over r to the 4th, and this is called an octupole. So you may wonder, like, if there is any systematical way to count all these orders, like, how should we make use of this to analyze the far field expansion? Or so let's now try to look at the problem with the general charge distribution. So the problem I'm going to consider here is say there's a arbitrary shaped object here, and there is a charge distribution in this in this strange shaped object, but the size of this object is limited, and we are trying to figure out what is the potential far away from this object. So here this is the point of interest. And say here this is the origin of our coordinate system, and then this one is the r vector. And here, because there are charge distributions on this object, and we are interested in integrating them over, and so there is a source coordinate. And the source coordinate is r prime. And then we also have the separation vector. The separation vector here is the difference between r and r prime, which we denote this as curly r. And we try to first give this differential charge. So for this volume, there is a charge, and we try to integrate over this volume. Now, because we are in the far field limit, so this R prime is a small quantity comparing to R. Then this separation vector, if we write the square of the separation vector, that is simply the R square plus R prime square minus 2R R prime cosine theta. Take this as a prime. So the cosine theta is simply this angle theta prime is the angle between this R and R prime, and this is the law of cosine. And because this R prime is a really small quantity, we can write R prime over R as a small value. So let's try to do this. We see that here not only the R prime over R square is small, also R prime over R times cosine theta prime is a small quantity. And now we can simply define this small quantity as epsilon, and now this separation vector actually can be written as 1 plus epsilon, and here I've taken a square root of this expression. This simply means. Now let's see what the potential looks like. So the potential of this system is simply V equals 4 pi epsilon naught integrating over the curly R. So this should be the times the distribution of the charge at R prime, and integrating over the tau prime, which is the volume element. So we are interested in to see how this separation vector, 1 over separation vector, behaves when this quantity is small. So let's do a Taylor expansion of this result. So this here, 1 over curly R should be 1 over R times 1 plus epsilon to the power of 1/2. And this one can be Taylor expanded. So the result should be so this is the zeroth order. This is the zeroth order. This is the first order. The 1/2 is simply taking the first derivative of this expression, and now you have to take the second derivative, but also divide by 2 factorial, and you have to take the third derivative and calculate divide by 3 factorial. And this expression actually goes on and on. And here, if we don't truncate this expression here is exact. Now let's actually plug in this epsilon and see what we can get. So remember this epsilon is the expression over here. Okay, so the first term is keeps the same. So the second term, let's try to write this epsilon as r prime over r times r prime over r minus 2 cosine theta prime. Now if we do this, I'm trying to write out this epsilon here, and I also need this epsilon square, which correspond to the first term square and the second term square. Now let's write one more term, which is 2 terms cubed. And I'll stop here. And now let's try to see if we can collect them in terms of cosine theta prime. So the 0th order of cosine theta prime has a term here that should be 1. Let me see. And okay, and so there are also terms that involves r prime over r and r prime over r. So this term is r prime over r squared, but this term is of a lower order. So we also need to try to collect. So it actually makes sense to collect terms in order in terms of r prime over r instead, because r prime over r is what's really small, and we should actually expand in terms of r prime over r first. And so the 0th order of r prime over r is 1, and the next leading order should be r prime over r times cosine theta prime. So the first order is now the rest of the terms contains higher order of r prime over r. So let's see. So the next order is r prime over r to the power of 2. Here we can see that this is a term contributing, and there is also the term over here that's contributing, and all the other terms are at least of order of r prime over r to the cube. So let's write this out. So here 2 square gives 4, and the second term simply gives 2 over 3 cosine theta prime square, and the first term gives minus half. And now let's do one more step and try to calculate the power of r prime over r to the power of 3. And again, let's see. So there is one term contribute from here, and also one term contributing from here. So here this contributes cosine theta prime to the cube, and here there is a contribution of cosine theta prime. So let's see. So the result should be 2 over 5 cosine theta q. So that's from the last term. And also the 2 over 3 cosine theta prime. Let's stop here, but in principle, there are all higher order terms. Now this expression seems a bit long and tedious, but I don't know if you remember anything. But here, this is actually P0 cosine theta, which is the zeroth order of the Legendre polynomial. And this term is actually the P1 cosine theta, which is the first term of the Legendre polynomial. And magically, this term is actually the P2 cosine theta. And this term is the P3 cosine theta. So it seems all like magic, and if you don't believe me, you can go to fourth order, and the result is actually extremely simple and compact. So the nth order coefficient should actually be the simply the Pn cosine theta prime, and so this expression is actually proves mathematically that the coefficient of this Taylor expansion in terms of r prime over r, this Pn cosine theta is actually its coefficient, and this is actually called the generating functions in mathematics. And but you don't need to remember that. You simply need to know the conclusion that 1 over curly r actually can be nicely expanded into this compact form. Given that over curly r is expanded, and expansion is any n. And I simply plug the expression of this 1 over curly r, and which gives go to 0 to infinity. And the power of 1 over Rn plus 1, and can be put outside of the integral, because we are integrating over the r prime, which is the source volume element. And so here the r prime goes to the order of n instead of n plus 1. And then this is the Pn cosine theta prime, and also the charge density distribution rho r prime, and integrating over all the volumes. Now let's write down explicitly for a few orders. So for the 0th order, we simply plug in P0 cosine theta, which is a constant. So it's integrating n to the 0, so both two terms vanish. So it's integrating over r prime only. And then the second term begins with 1 over r squared. And now we can see that there is an r prime contributing, and the P1 cosine theta is the cosine theta prime. Sorry. And then we need to add this density distribution. And let's write down one more term. So it begins with 1 over r cubed, and then there is r prime squared, and also this 3 over 2 cosine theta prime squared minus half, and times rho r prime d tau prime. Now we can identify here that this first term is actually the charge of the system, and the first term is proportional to 1 over r in the far field limit, and so we call the first term as the monopole contribution. And then the second term here we call this as a dipole, because it decays as 1 over r squared, and likely we call the last term as the term of the quadrupole, because it decays as 1 over r cubed. So you can actually check your homework to see in homework 1 if you really obtained a dipole just as I claimed here. So what I claim here is that now instead of working on this far field expansion of a very complicated distribution of V, now what you can do is you can simply integrate first this charge distribution according to the formula over here. So you integrate over the first. So in your homework 1 problem that's considering 2 spheres, you integrate the density of the first square times r prime and cosine theta, and then this, and also plus also add your term of this negative charged ball, and the two terms together will give the single expression on the right, and then you can simply multiply your answer by 1 over r squared. That's actually is giving your far field approximation. Do you have any question?
Why is there monopole, dipole, quadrupole, but there is no tripole? Like,
oh, you mean like so you can see here that here you can kind of see the pattern. So the monopole is one single charge of plus, and the dipole is one charge plus with another charge of minus. And now what this dipole does is it's trying to have a leading order of the monopole to be 0. So you have to construct in a way such that the monopole term here, the total charge is cancelled. So that's how you construct the dipole. So if you bring two close charges together, the total charge is 0, but there is a dipole term contributing to the system. And now if you want to go to the next step, you must have a system such that the dipole moment of the system is 0. So if you add only one charge, it first is not able to cancel out the monopole maybe. So say that if you want to if you somehow magically cancel out the monopole by doing something like q plus q plus q and minus 2q, then this kind of configuration is possible, uh, but here is slightly different from the three charge configuration. So here this form is also might also be a quadrupole, but they don't have an even charge. So if you calculate this term, I guess this one has you can think of you are bringing together two dipoles. So this one actually also is a quadrupole, but it has three charge, but the three charge has different amplitude. And if you have the same amplitude, then there cannot be a zero monopole term. Okay, so if we go without check